rules for all the trig and calc and square root functions that I said we couldn't do yet. So today what we're going to do is we're going to hit the substitution rule. There are two parts to it, and honestly this is a big part of integration. So you have to be able to use the substitution rule just like you had to be able to use the chain rule for derivatives. So the substitution rule is basically the chain rule for integration. So when we had the chain rule for derivatives, it was very important. We spent many, many days on it. Well, with substitution and calc, we're going to spend many, many days on it. So if you look down at your handout, it's not quite what's on my handout yet because I added an example in on yours to get you thinking about these types of problems. So go ahead, take a minute and see if you can answer or start to differentiate the antiderivative formula down below. So you have the integral of u to the negative 1 du, and it says it equals the natural log of u. How could we verify that? So I gave you the antiderivative to the derivative. How could you verify it backwards?
Well, the power of the formula just says the integral of u to the negative 1 du equals root du, which is the u plus c.
Yes. So what I want you to do though is go the other way. Like I want you to take and derive it to get the 1 over u. So do you remember when we actually derived those last time? We said, okay, if it's 1 over u, what do we have to also multiply by? So if I derive this, it's 1 over u times du dx. And the derivative of a constant is 0. So the important piece of information that we're looking at here is that du dx. And that's going to play an important role as we work through today. Because today we're going to need that du dx to help us with our substitution and anti-differentiation rules going backwards. So what we're doing is we're still making that connection between derivatives and integrals, moving forwards and backwards. If this was your original, this is your derivative. This is your original, that's your antiderivative. Okay. So at the top of the next page, it says if you integrate f of u du and you integrate f of u dx, are they the same? So again, if you integrate the function f of u du and you integrate f of u dx, would they be the same? Let's suppose that u is x cubed. And let's suppose that f of u is u cubed. So if we came up with a connection for this, if f of u is u cubed, what's f prime of u? If I wanted to find f of x, and I know that u is x cubed, then if I replaced my u's with x squared, f of x squared would equal x squared to the third. So f of x squared would equal x to the sixth. change our notation over here. When I integrated this function f of u, it was kind of like saying in Leibniz notation, let's say df du. Right. So instead of saying f prime, I could have said df du. And down here, if I were to integrate f prime of x squared, I get 6x to the fifth. Once again, if I wanted to change my notation, kind of be like saying df dx equals 6x to the fifth. Well, how does that help me put into place the integrals? Well, I need to know that I can get to that du. So I need to almost take this piece here, and I need to solve for du. I need to take this piece here, and I need to solve for dx. So I can put the du's and the dx's into my problem. Because at the moment, sure, I know f of u. F of u is u cubed. So I have the integral of u cubed du. So it's the antiderivative of u cubed du. Okay, and then plus our imaginary c. But over here, I have f of u dx. So if I were to integrate that, I have to substitute out one with the other. So I could either replace the dx with the 6x to the fifth by solving for it here, or I have to replace f of u with f of u with an x in there. So we said f of u was u cubed. We said f of x squared was x to the sixth. I need some sort of connection, though, to get f of u in terms of x squared and not being x squared. So go back to the idea that u equals x squared. And here, you could just replace that with the x squared and still see that that's why you get x to the sixth. So f of u is equal to f of x squared. So over here, what do you get when you antiderive? Can we make a connection between u to the fourth and x to the seventh? What could I do over here with this u? What do I know about u? So we could say that this is 1/4 x squared to the fourth, let's see. Is this going to equal that? No. So that's where the substitution that we want to do isn't always going to work, and that's why I kind of hate you going into the derivatives. We have, the idea behind the substitution is that you have to replace them before you integrate them. Because if you replace after integration, they're not equal. If you go back and you think about like the chain rule and some of the other properties, we said the same thing with like the product rule and the quotient rule. You couldn't replace them before, you had to replace them after. So the idea is that substitution needs to occur before, not after. So let's look down at the most simple basic chain rule problem we used to do. If we had a square root, then we knew we had to take the derivative of the outside and multiply it by the derivative of the inside. Well, now what we're going to do is we're going to take out the complicated part of the square root. We're going to get rid of the 2x plus 1. So we're going to say, okay, u is 2x plus 1. And here's what I said, you cannot integrate with mismatched variables. If I replace this integral, so it's the square root of u, I cannot keep it dx. I have to use substitution and get rid of the dx. And in the example above, we tried to integrate with mixed variables, and we saw that it didn't give us that same answer. So what you're going to do to get rid of dx and to replace it with du, you're going to derive this using Leibniz notation. So we would say derivative of u with respect to x, so du dx, is 2. Now, you've got to solve for dx so that you can replace this dx with dx. So you're going to flip-flop the 2 and the dx. So we'll say du divided by 2 equals dx. Now I can replace the dx and the dx with du divided by 2. Now you know how to integrate the square root of u. You know how to change this. The 1/2 gets brought out in front, right, because a constant comes out. We change the square root to u to the 1/2 du. And then you go and say, okay, I add 1 and divide by my new exponents. So you have 1/2 u to the 3/2 divided by 3/2. Clean up your fractions. So 3/2 is really like 2/3, but 2/3 times 1/2 is really like 1/3. So you get 1/3 u to the 3/2 plus c. Now it says that we started the problem with x's. We're going to finish the problem with x's. So we're going to go back and substitute one more time and replace u with the 2x again. So you get 1/3 2x plus 1 to the 3/2 power plus c. So we're substituting in, replacing, and then substituting back. So you'll go from x's to u's and then back to x's. Okay, example 2. We have x over the square root of 1 minus 4x squared. So once again, what's the complicated part? Where is there a function in a function? Yeah, in the denominator. The function in the function is the 1 minus 4x squared. So we're going to substitute out the 1 minus 4x squared and replace it with a u. You're not taking the square root, you're just taking what's under the square root. And then we say, okay, what's du dx? So derivative of 1 is 0. Derivative of negative 4x squared is negative 8x. Solve it so that you can isolate the dx's together. But what do you notice about the numerator in this problem versus the last problem? This one now has an x above. So if I plug this in, my u here, at the moment I have x dx over the square root of u. So when I substitute in, I'm actually looking for an x dx to replace with the du, not just the dx, because I got to get rid of the x that's in this numerator as well. So when I solve, I'm solving for all of this, which means I'm dividing simply by negative 8. So I'm going to replace x dx with negative 1 over 8 du. So that my integral becomes negative 1 over 8. Remember, we love to pull out constants. I'm going to bring my square root up as a negative exponent. So I get negative 1/8 u to the negative 1/2 du. And now I simply antiderive. So I add 1 back, divide by my new exponent. Let's see. Clean up the 1/8 and the 1/2, so you multiply by 2. So you get negative 2/8 or negative 1/4, the square root of u plus c. And then lastly, we're going to back substitute out the u. So you get negative 1/4, the square root of 1 minus 4x squared plus c. All right. Remember, you want to replace the complicated pieces. So I want to get rid of what's under the radical. So let my u be 1 plus x squared. Then my du becomes 2x dx. That's kind of harmful though, right? I don't need a 2x. What do I need? And 5. So this is where substitution starts to get a little, we have to finesse them even more. We're going to take the idea that this line here can be reversed and solved for x. So take this and make it u minus 1.
Logan Almo, please come to the office. Logan Almo, please come to the office.
So if u minus 1 is x squared, that gives me at least 2 more x's back. I have at least 1x right here. So I can also say that half of u, or half of du, is x dx. So I have 1. Now I have 2 more, so I have 3. How many more do I need to get rid of? Yeah. So what could I do to this to add it or make it 2 more? If I square, then I get u minus 1 squared equals x sub 4. So now I have here, I have the singular x. Down here, I have 4 x's. So now when I replace this, I have the square root of u. I have u minus 1 squared. And I have half of u du. Half of du.
Natalie Lovejack, please report to the office. Natalie Lovejack to the office.
How can I clean this up? Because there's not really an antiderivative product rule. Yeah, so what we're going to do is you have to square the FOIL, the u minus 1, and then distribute the square root. So here's where the algebra really plays a role in the calc. That becomes u to the 1/2. u minus 1 squared becomes u squared minus 2u plus 1. And be careful, like what I noticed on our quizzes is we tagged along the du and the integrals, and sometimes we tagged them along too far, and then sometimes we didn't tag them along far enough. So start paying attention that, like, as I have not yet taken the integral, the du and the integral sign come with me. We're going to distribute one more time. So 1/2 times 2 is really like adding them together. You don't actually multiply. It's like 2.5 or 5/2. That's what's tricky. That's where we kind of make our mistakes. This is like 1 plus 1/2, so 3/2. Plus u to the 1/2. So as of right now, all I've done is apply algebra. I have not yet taken the integral. In the next line, I'm going to take the integral, which means I drop the integration sign as well as the du symbol. The integration sign and the du symbol are gone. Follow your rule. Add 1 to this exponent. So that's like adding 2 over 2, right? So that's going to give me u to the 7/2. And I'm just going to flip my fraction now. Remember, you could write divided by 7/2, but that's the same as multiplying by 2/7. Minus, this is going to become 5/2. And now you have to multiply 2 by 2/5. So I get 4/5. 1/2 will become 3/2, just like multiplying by 2/3. And after all of this, I still have to initiate and include my, distribute your 1/2. And since I'm running out of space, I'm going to plug back in my original u. So 1/2 times 2/7 becomes 1/7. One plus x squared to the 7/2 minus 1/2 times 4/5, which is 2/5. 1 plus x squared to the 5/2. Plus 1/2 times 2/3, which is 1/3, 1 plus x squared to the 3/2 plus c. Okay, I want to stop here. The next examples have numbers, which means they're going to get numbers for answers. And I want to keep everything general and plus C for your homework and work. So that is it. Good.